Okay, so let's take a look at an example using this. Let's say we have a current carrying wire, and our current carrying wire has a current of 5 amps, and we have point C. I don't know. Oh, I know why it's C. It's because I'm getting this from another problem that has other questions about points A, B, D, and E. Point C is 5 millimeters. From the center of the wire. So that makes more sense there. That's to the center of the wire. And my question is, what is the magnitude of the magnetic field at this point? So what is the magnitude of the magnetic field at this point? It looks like we need to know a little bit more, so it must come from a previous problem.
No. We have everything. 5 millimeters is the radius.
Yeah, we have everything. Yep.
What are we looking for?
We're looking for the magnitude of the magnetic field. Okay, so the first thing y'all notice that you definitely had to change that to meters, which was 5 times 10 to the negative 3 meters. And then you just plugged in with all these constants. One nice thing that you'll notice with the 2 pi here and the 4 pi is that your pi's often cancel out, which can be handy. And when you do this, you should have gotten a magnetic field of
That's a 4.
Okay, as long as it's a 4, then yes.
2 times 10 to the negative 4
It looked like a 10 from here.
Teslas. Okay, using the same wire, let's assume that we have a positive charge right here at point C. We have a positive charge, and this positive charge is moving in the same direction of the current, as the current. Positive charge is moving in the same direction of the current, and the positive charge is Q equals 1.0 microcoulombs. And I would like to know the force on that charge. Now, this combines our 2 topics. The topic we just learned was figuring out the magnetic force caused by a current. And then our previous topic is what is the force on a moving charge due to a magnetic field. So we broke this up in 2 parts, so that made it a little easier to see what was going on. We already have the magnitude of the magnetic field here because y'all did an excellent job on that. But now we also need to know the direction of that magnetic field, and I have not taught y'all that. And so here's how you find the direction of the magnetic field from a current carrying wire. So here's our current carrying wire, and it's a different version of the right-hand rule. And here's how this right-hand rule works. The magnetic field, if you notice, it depends on the distance from the wire. And the magnetic field is going to go in circles around your wire, and it'll be smaller the further you go out. So the magnetic field is not in the same direction everywhere. It depends on where you are. So those are circles, and here's how you figure out how it works. You point your thumb in the direction of the current, and then your fingers will curl around the wire in the direction of the magnetic field. And so if you're trying to figure out the direction of the magnetic field at a particular point, then you figure out what direction would your fingers be pointing at that point. So in this example, if our thumb is pointing in the direction of the current, then at point C, which is above, so here's our wire. At point C, which is above our wire right here, our fingers are coming out of the page. So do it like you're in your page, you've got your current carrying wire, and then you curl, so it's coming out of the page. So at point C, we now know that our field has magnitude 2 times 10 to the negative 4th, and the magnetic field is coming out of the page, right there. So now that we know that, can you figure out the force on the charge? And to do that, we have to go back to our previous formula, which is that F equals QV B sine theta, but luckily we're perpendicular. It was a moving positive charge.
Yep.
What's micro? 10 to the negative 6. Did I give a velocity for this charge? Oh, we probably need that. It's a velocity of 5 meters per second. So times 5 meters per second. That was coulombs. Times 2 times 10 to the negative 4th Teslas. 10. It should be
Just 10 to the minus 9.
It should be just 10 to the minus 9.
We use a big sponge.
You're supposed to. Let's do another one. And this one
I don't know what it is, but it was sparkling, so I had to.
is a typical kind of problem. Oh, I'll show you what that is. Okay, so we have this little device here. Very cool. You take the lid off, and then you slide these things down, and you get little scissors. Isn't that cute? Okay, this kind of question is one that you, thank you, you will most likely see because they like to ask them. So here I have 2 current carrying wires. Okay, so I have 2 current carrying wires. Currents are equal. I'm not telling you what they are, but they are equal. Current in wire 1 equals current in wire 2. But they're moving in opposite directions. And so the question is, how will these wires interact? And your answer choices are things like they will attract each other, they will not affect each other, they will repel each other. You need to know the length of each wire, or you need to know the current in each wire. And so those are your answer choices. So what you have to do is use both of our rules to figure out the force, the magnetic field created by a wire, and then what does that magnetic field do to the other wire. So if we start with the wire on the left, and we point our thumb in the direction of the current, and we curl our fingers around, we see that when we get to the other wire, our magnetic field is going into the page. So the magnetic field produced by the first wire causes a magnetic field going into the page here. Okay, so now we use our rule on F equals IL cross B equals ILB sine theta, and sine theta here is 1, to figure out what that force does on that current. So to figure that out, we point our fingers in the direction of the current, and then we curl our fingers in the direction of the magnetic field. Magnetic field is going into the page, and our thumb is now pointing to the right, so this second wire experiences a force to the right. Okay, now we have to do the same thing with the first wire. So we now figure out the magnetic field produced by the second wire. So to figure out the magnetic field produced by the second wire, you hold your thumb in the direction of the current, you curl your fingers, and that shows you the direction of the magnetic field. So we see that the magnetic field on the first wire is also into the page.
Oh, right.
Yeah, use your right hand. Okay, now once we know that that magnetic field is into the page, we try to figure out the direction of the force on it. And so to figure out the direction of the force on it, we hold our thumb in the direction of the current, and then we hold our fingers in the direction of the current, our fingers in the direction of the current, and then we curl in the direction of the magnetic field, which is into the page, and we see that our force is to the left. And so that means that this one experiences a force to the left. So the correct answer choice on this is that they repel each other.
After you did one of the wires, couldn't you just figure that the other one was like equal to opposite?
You could. I would still go ahead and do it just to be on the safe side, because what I'd like y'all to do on your own now is to figure out what happens if you have two wires that have an equal current in the same direction. So figure out, and then you have the same answer choices on that. So y'all do that one on your own, and then tell me what you get. What did y'all get for your answer on doing this?
I hope they attract each other.
What's that?
They attract each other.
They attract each other. Good.
Did they attract each other? Awesome.
They do. Okay.
Why? I mean,